Hi everyone, my name is Michael Mullen, and I would like to do a little quickie video for you about the speed of WASM. So how slow is WASM when compared to native code? So I was tooling around on the YouTubes a few days ago, and I came across a video by this guy called Chris Hay. Um, and I'm going to give Chris the highest praise I can possibly give another YouTuber in that he inspired me to learn a new thing. And that's the entire reason why I love YouTube, because YouTube, when I come across videos like Chris, it inspires me to learn new things, and I love learning new things. So, in Chris's video, what he discusses is compiling Rust code into WASM and using the WASI kind of interoperability libraries, I guess you call them, to be able to run WASI on like a command line, that sort of thing. Um, and one of the one of the kind of things that really stuck out in my mind is in Chris's video, he quotes the inventor of Docker. And I'm going to kind of paraphrase the quote here, but the idea is that at the time the creator of Docker was creating Docker, he wouldn't have needed to do this if WASI and WASM existed at that point in time, because WASI and WASM address all of the concerns that Docker was originally made to work on. So if you want to get more deep into this, please go watch Chris's video. It's very inspiring. It's very good. Chris is a very good YouTuber. He's got high quality videos, much more high quality than mine. And yeah, he kind of goes through the process of taking some Rust code and turning it into WASM code, and then running it through some runtime systems called WASMer and WASM time. So please go watch his video, and I'm going to assume that you've got the knowledge that Chris goes through in his video in my video here, because there's no sense in me kind of repeating on things that he's already done at an expert level. So yeah, the thing is though, WASM is not native code. WASM is bytecode that is run through an interpreter. And bytecode historically has been slower than native code. So, when running a Docker image on a Linux system, the things inside of that Docker, that OSI container, if they are compiled up from Rust or from C or C++, they are running native code on that Linux system. They just have constraints about what they can do. While WASM run through WASMer is bytecode run through an interpreter. So obviously, on a Linux system, there's going to be a performance difference between running a Docker container containing native Rust code and running a WASM file. Yeah, and I wanted to know what the performance difference is between native Rust and WASM. And then while I was at it, I was like, oh, what's the difference between Rust, WASM, Python, and Go? What while I'm at it, let's take a look at that sort of stuff. So I'm going to be doing some poor man's performance testing just by using the Linux time command here, rather than going into Criterion or any other kind of more detailed, more precise benchmarking utilities. For my concerns right now, time is good enough. The time utility is good enough to kind of give me a feel for the performance differences between these different things. And while I'm going through this performance testing, you're going to notice that one language is a lot faster than you expect, and another language is a lot slower than what you expect. But anyways, yeah, let me just kind of jump into the tests and we can see what the heck I'm babbling about here. So I've got some applications here, and this application written in Rust here in my right hand side of my window here is a little Rust program that creates a vector of 1,000,000 in size, and it contains I64 values ranging between 0 and 99. Um, and then what I'm going to do is after I get that random vector, um, it's unsorted. So I'm going to 250 times in a row, I'm going to copy that vector into a new vector and sort that new vector. And then we're going to see kind of how long it takes to do this work. So yeah, let me compile this up and we can compare native code to WASM code. So let me just do the work here. So cargo, build, release. So we're going to compile up our native code here. And then I'm going to use time to kind of give myself a poor man's benchmark. And we can see it took about 13 seconds to complete all of these clonings and the sorting, um, and of course the initial make of the unsorted vector. So let's compile up the WASM code and see how long that takes. So again, to learn about all of the compiling and stuff like that, please check out Chris's video. Not only is it very good, but it's inspiring, and YouTube is all about being inspired. So please go watch it. So we've compiled it up, and now let's give it a run through the WASMer runtime. So this time in WASM, it only took 15 seconds. That's pretty good. I don't want to directly compare these two things because, unfortunately, because of my poor man's benchmarking here, I'm not only testing the speed of this program, but I'm also testing the speed that WASMer starts up. There's a startup cost to running WASMer, and that's not really fair as a comparison. I need to get rid of that. And near the end of the video, I will up my amount of iterations here to more normalize the startup time of WASMer. You can see that WASM time, it should take a similar amount of time to WASMer here. So it's around the same amount of time, 15 seconds, a little bit less, a little bit more. If I did a proper benchmark where I ran these things, 100 times in a row, I'd get better values. I'd get more accurate values for this sort of thing. But my intention here is just to see, like, is WASM on the scale of native Rust? It's pretty close. We'll get to this in a second. Now, my next question was, okay, how fast is Python? So I wrote a little Python script to do basically the same thing. So in here, I'm going through 1,000,000 times, building up a list of values between 0 and 99. I copy the list and then I sort the copied list 250 times. So let's do let's give Python a poor man's benchmark here. So Python strangely is pretty darn fast. It's in the same realm of WASM code. Um, why is that? The reason for this is twofold. First of all, I'm not really fully running Python code here. The sorting routine for Python is actually written in C. So I'm kind of cheating but not cheating because Python does a lot of this sort of drop down into C to do expensive work. But yeah, the other reason is that actually I'll get to the other reason after I run some Go code. So I did the same sort of algorithm with Go here. And let me get to that code. Um, so Go is basically the same. I've got this function that will build me up a slice of 1,000,000 in length, and it will have values between 0 and 99. And then I will copy this into a new slice and sort that new slice. Now pay attention in that I'm using the stable sort. It's important that I'm using the stable sort, and I know I keep saying this a lot, but I will get back to what that means in a second. So time main. So as you can see, Go is a whole lot slower than even Python. So something's fishy going on here, right? So this is what I meant by, let me get back to the what's so special about Python. So first of all, the Python sorting routine is actually written in C, and the Python sorting routine is a very performant sorting routine called Timsort. Timsort is an extraordinarily performant stable sorting routine, and Go is not using Timsort. The way that Timsort works, and maybe this will help you understand why the Python sorting routine is so quick. The way that Timsort works is that you've got your array, your slice, your vector of 1,000,000 in length. Timsort goes through a first pass over the items in that list, and it sees for any natural runs. What these natural runs are is already sorted sections inside of the list. So if it sees like part of the list where the items are 1, 2, 3, 4, 5, 6, 7, 6, it will go that 1, 2, 3, 4, 5, 6, 7 is naturally sorted. I don't need to ever sort that again. I'm going to take that kind of area. I'm going to remember where the starting point is, the ending point, that sort of thing, and I'm going to call that a run. It then goes the 6, and then it might be 6, 6, 5, 4, 3, 2, 1 is the next area inside of the list. And it's going to go, this 2 is a run, and it's in reverse. So I'm going to flip that around in place, And now I have a 1, 2, 3, 4, 5, 6 run, and it is already sorted. So now I have two already sorted areas inside of this list based on my first look through it. It does a few more optimizations where it goes, this section here goes 1, 3, 5, 4, 2, 8, 6, 9, 3, 9, 2, 4, 5. It goes, okay, this section is not sorted, but it's small enough that doing an insertion sort is actually quicker than doing any other type of sort because of not needing to kind of go through the merging procedures of a merge sort. So Timsort, when you get down to it, it turns into a merge sort, and merge sorts, of course, have a little bit of overhead because they have memory constraints and they kind of need to copy data around a little bit to do the merges properly. So if it finds a section that is unsorted but it's small enough, it can do an insertion sort, which is very fast for small amounts for a small list. So it sorts that using insertion sort, and then it goes, okay, now I have another run inside of the list that is already sorted. So once it goes through the list the first time, it's got these sections of runs. And then it goes through its merge routine, which if you're familiar with merge sort, it's basically the merge for merge sort. And it joins all these runs together. And this guy called Tim, which apparently is a sorting genius, created this extraordinarily fast, stable sorting routine. And that's why Python is so fast at sorting. So first of all, it's written in C. Second of all, it's using this amazing stable algorithm. What you should be asking right now is, why does Michael, me, keep saying the word stable? Stable doesn't mean it'll break or not. A stable sorting routine is a sorting routine which keeps it keeps its previous sort if two items are equal. So what this means is, say you're not just sorting integers, but you're sorting like a table of data, and this table of data is for employees, and the fields in this table are for the employee's first name, the employee's last name, the employee's age, and the employee's start date from when they started working at the organization. What a stable sort does is you can go through a stable sort and sort based on last name. And so you've got your list in a certain order based on sorting for last name. Later on, you might want to sort again for age, but you also want to kind of keep the previous sort in mind when you're sorting for age, so that when you come to two employees that have the same age, the employee that is first in the list is the employee with the last name that starts with A rather than Z, that sort of thing. That's what a stable sort does. An unstable sort gives no guarantees on that. It's just gonna plop things down based on age, and it doesn't care what happened before. This means that an unstable sort can be much faster than a stable sort, but there are more reasons to use a stable sort, especially when it comes to kind of conceptualizing and understanding data for human beings. So, I don't know if Python itself has an unstable sort, but as you can see, its stable Timsort is very, very fast. And that's why I wanted to point out that I'm comparing against Go's stable sort. Let's take away Go's stable sort, and because we're only sorting integers here, we don't care about stability. We only care about the sorting of those integers. And let's see how fast we can get Go using an unstable sorting routine. So let's go back in here, recompile, and rerun using an unstable sorting routine. So there we go. That's much better. 12 and a half seconds is a whole lot better than 55 seconds for doing a sort. This sort that that Go uses is a quick sort, and it's when I looked through the code, I didn't see anything special about this quick sort. It looks to be like a pretty run-of-the-mill quick sort, but quick sort is appropriately named quick. So yeah, I don't know if Python has an unstable sorting routine, but Rust does. So let's take a look at Rust's unstable sorting routine. So I'm going to change this sort here to a sort unstable, and we shall see how fast we can get our Rust code. So first of all, let's just do WASI, because it's higher up in my command line history here. And we'll run this through WASI time this time, and we'll see how fast it takes us to get through doing. Oh wow. So that's pretty fast. Less than 3 seconds. What about native? Let's see how fast we can get our native going. So it's even faster there. So yeah, Rust is pretty fast, and if anyone tells you Rust isn't fast, they're wrong. A Rust unstable sort is significantly quicker than Go's unstable sort. Now, I am being a little bit unfair. First of all, Rust's stable sort uses Timsort as well, but written in Rust. You can take a look at Rust's stable sort by doing a lookup in Google for Rust slice sort, and then we'll go into Rust here and then do a search for sort. And then if we click on sort here, what you can do is click on source here. It will take you to the sort, and it will take you to a merge sort. And lucky for us, merge sort is actually contained in this file, so it's really easy to look at. So if you wanted to understand a little bit more about Timsort, take a look here. This is easy to understand, easily readable Rust code, so long as you understand Rust. But yeah, Rust's stable sort uses Timsort, and I haven't looked deeply into their unstable, but they use what is called a pattern defeating quicksort. So I'm not very familiar with that. I haven't looked through the code, but as you can see, it's pretty quick. It's fast. It's fast in WASM. So yeah, that kind of compares like the different languages. It shows off like how fast WASM can really be. But let's try and take away as much as we can the amount of time that WASM time or WASMer takes up during its initialization phase. And we're going to do that by just making us do more runs over the sorting routine and the copying of the vector here in order to kind of make the sorting routine and the copying of data more prevalent in our output than therefore making the initialization time of WASM time or WASMer less meaningful in our data set. Again, this is still a poor man's way of doing performance testing, but kind of gives a good idea of what's going on here. So I've upped my amount of iterations here, and I will give us a compile and build, this time WASI first. And let's run it with WASMer. So 22 and a half seconds. That's pretty fast, I think. Let's compare it against native code. And I'm going to get out my calculator here so we can do a quick napkin math to see just how much faster native code is versus WASM code. So 22.4 divided by 16.7 equals 1.34. So WASM code is roughly, native code is roughly 2/3 the speed, the time. It takes native code 2/3 the amount of time it takes WASM code to run. So that is like 33% is it's an overhead. That is something that you need to think about. If you're writing a if you're writing a web server, if you're writing a Rust web server, and it needs to be high performance and it needs to handle a lot of clients, a 33% overhead due to WASM is going to cost you a significant amount of money if you put that code in the cloud and you rely on the cloud to spin up more instances of your web server in order to meet the demand that your clients are placing upon you. Yeah. So there is some overhead here. However, it's already pretty darn fast, right? If you were kind of deciding whether you wanted to load up WASM code with Rust versus Python code, well, you've got something to think about here. Your Python code, if you containerize your Python code, the bundle that you need to ship is going to be pretty large, because if you create an OSI container, not only do you have to put your Python script inside of that OSI container, but you have to put the entire Python ecosystem inside of that container, and that can get up into the hundreds of megabytes in size. So that's rather than your WASM code, which my WASM code here. So this is the native code. It's 299K in size, and the WASM code, this is going to surprise you, I think. The WASM code is only 69 kilobytes in size. So this WASM code, if compiled under the correct compiler flags, can get pretty darn small here. Of course, you also have to throw in WASMer, right? So how big is WASMer? 13 megabytes. Okay, 13 megabytes plus 69 kilobytes is bigger than 300 kilobytes. But of course, our TTT object, target release TTT, also requires us to throw in all of these libraries into our container as well. So you've got some sort of trade-offs here. But yeah, if you're kind of comparing whether you want to throw in Python versus WASM, you've got something to think about here because they are both on the order. They're similar. They're similar time frames. They're similar performance characteristics for this specific test. Like I said, with Python, there's some tricks that the Python developers have done by dropping down into C for a lot of cases to enhance their performance. Um, yeah, you've got stuff to think about. Um, Straight up native, it's slower and it's going to cost you money. WASM is getting better all the time. Um, let's hope that it keeps continuing and we get some more performance out of this. I hope you've learned something. I hope you've stuck around for all of my rambling. And I wish you a good day, a good evening, or a good morning. Thank you.